Hello, friends. Welcome to the first episode of Inorganic Chemistry series. In this series, we try to cover all of the theoretical concepts of inorganic chemistry which you will need. And our focus is on the most important, or let's say, most practical and useful areas of inorganic chemistry. So, knowing this fact, we might increase the pace of the videos at some parts so we can put a great amount of attention on the concepts and on the chapters which are more practical. Let's waste no more time. Don't forget to subscribe to ChemXplain and let's start this video. We want to start with historical development of atomic theory. When you clicked on this video, you basically are familiar with some different atomic theories which have been provided by different scientists. But we want to start from the very first theories that have been provided by Democritus and Epicurus. You know, these two scientists, they provided really basic concepts and basic, let's say, theories about the atomic structures. And those concepts are not really useful and practical these days. So let's move a little forward about the year 1808 when John Dalton published a new system of chemical philosophy that he talked about the new atomic theory. Well, let's have one of the most important principles of John Dalton's theory. It says, the ultimate particles of all homogeneous bodies are perfectly alike in weight, figure, and etc. In other words, every particle of water is like every other particle of water. Every particle of hydrogen is like every other particle of hydrogen, and etc. So let's make it a little more simple and understandable. So let's assume that we have a glass of water here. And with your knowledge, I mean in year 2024 or whenever that you're watching this video, we know that water consists of H2O molecules, but at that time that John Dalton was publishing his book, he thought that water is not consist of H2O molecules. He thought that water consists of water particles. I mean, every other water particle that you pick from this glass of water are exactly identical and similar. And there is no difference between any other particle that you can find in this species. That's great. Let's move to another principle of Dalton's theory. He also thought that atoms combine in simple numerical ratios to form compounds. The terminology he used has been modified many times for sure, but we can say that he clearly presented the concepts of atom and molecules. For example, in describing the reaction between the gases hydrogen and oxygen to form water, Dalton said that when two measures of hydrogen, so two measures of hydrogen, and one of oxygen gas are mixed and fired by the electric spark, the whole is converted into steam. And if the pressure is high enough, this steam becomes water. So it is most probable that there is the same number of particles in two measures of hydrogen as in one of oxygen. That's great, but let's be careful that Dalton didn't know about the diatomic nature of the molecules. Today we know that hydrogen molecules are H2 and oxygen molecules are O2, but Dalton was not aware of this. And because of this, he assumed that hydrogen and oxygen gases are monoatomic. And all of these together made this conclusion for him that the formula of water is something like HO, which today we know is not accurate. And the formula and the reaction that today we have for forming water from hydrogen gas and oxygen is 2 hydrogen molecules plus 1 oxygen molecule gives us 2 water molecules. That's great, but John Dalton's theory is enough for now. Let's move one step forward. Since then, many scientists use their different and own numbers for molecular formulas and weights. And all of these things led to many confusions, and no obvious progress has been made in those years. And this continued until 1869, which two scientists, Mendeleev and Meyer, independently proposed periodic tables nearly like those used today. And from that time, the development of atomic theory progressed rapidly. Now, let's see what the periodic table is. Well, the idea of arranging the elements into a periodic table had been considered by many chemists, but either data to support the idea were insufficient or the classification schemes were incomplete. Mendeleev and Meyer organized the elements in order of atomic weight and then identified groups of elements with similar properties. By arranging these groups in rows and columns, and by considering similarities in chemical behavior as well as atomic weight, Mendeleev found vacancies in the table and was able to predict the properties of several elements such as gallium, scandium, germanium, and polonium that had not been yet discovered. When his predictions proved accurate, the concept of a periodic table was quickly accepted. The discovery of additional elements not known in Mendeleev's time and the synthesis of heavy elements have led to the modern periodic table. Great. In modern periodic table, a horizontal row of elements is called a period, and a vertical column is a group. The traditional designations of groups in the United States differ from those used in Europe. Well, the International Union of Pure and Applied Chemistry, which we can call IUPAC in short, has recommended that the groups be numbered 1 through 18. In this course, we will use primarily the IUPAC group numbers, and some sections of the periodic table have traditional names. That would be enough for this video, and I assume that you're somehow familiar with the concept of periodic table and the atomic theories, so I do not make this video longer. Thanks for your attention. So don't forget to subscribe to our channel and hit that thumbs up button if you found this video useful. Wait for us until we make the next episode of this series. Thank you so much. This is ChemXplain.